Today we'll be talking about free body diagrams. So I'm just going to work through a couple problems and I'm going to show you how to draw the free body diagrams for all the problems. So the first problem we have is find the normal force on the luggage case and the acceleration of the case. So we just want to find the normal force of the case and the acceleration and the direction of that acceleration, of course. So whenever you're drawing a free body diagram, you represent it as just a dot. And when you draw this dot, let's draw out all the force vectors being acted upon it. Well, there's the weight force. There's the weight force. There's also the force of the person pulling on the luggage. Okay, so we can write this F pull. And there's also the normal force, N. So we have in total 3 forces acting on this luggage case. And whenever you draw free body diagrams, you have to write the acceleration. But I'll just leave that for now since we haven't solved for the normal force yet. So in order to solve for the normal force, what do we need to know? Well, we need to know that this luggage case isn't accelerating in any direction, up or down. All right, if it was accelerating up, then it'd be flying. If it was accelerating down, then well, it'd be falling. It would be falling down to the core of the earth. So we know that the net force in the y direction specifically is equal to 0. What do we do with this information? Well, we can solve for all the y forces going on here. Well, here's the thing about this pulling force. This guy is pulling on the luggage case at a diagonal. So this diagonal force vector has 2 components. It has the x component and the y component. So we can actually solve for these components individually to know how much this force is contributing to each x or y axis. So if you just write down, let's say, this is equal to 120 newtons. Right? I think, you know what, I'm just going to remove the acceleration. It's distracting. I'll add that later. If you have 120 newtons here, times, at this diagonal direction, you can multiply this 120 by the sine of 45. And when you do that, you can actually get the y component of your force vector, which is 84.85 newtons. And if you multiply the x component, if you multiply 120 by the cosine, so let's actually note that down for you guys. This is 120 times the sine of 45. And if you do 120 times the cosine of 45, you get the same exact thing, 84.85 newtons. So in the y direction, this guy is pulling the suitcase upward slightly, and in the x direction, it's pulling the suitcase to the right. So he's pulling the suitcase up 84.85 newtons. And in theory, well, technically, if you're pulling up on something, this would make it not necessarily lighter, but it would experience the ground less. So that's a little hint of where I'm going to go next. What I'm going to do is just add up all the forces here, so we know if they're equal to 0 or not. So let's add up all the forces. We have the normal force in the y direction. Add up all the forces in the y direction. I said all the forces before, but we're adding up all the forces in the y direction. And if you add up all the forces in the y direction, you get the normal force. You get the y component of the diagonal pull, so that's 84.85 newtons. And we also get the weight force. But the weight force is going in the opposite direction, so both of these are, the normal force is pushing up, and the pull force is going up, so these are positive. But since the weight force is going in the negative direction, the weight force is going down, it's negative. So if you calculate the weight force, weight is just equal to mass times gravity. Therefore, the weight of this suitcase with the mass of 22 kilograms is just 22 times 9.8. This is 115.6 newtons. So the weight is 115.6 newtons. And what we can actually do is solve for the normal force here. Since we stated before, the luggage case is not accelerating in any direction, up or down, the net y force is equal to 0. So the total forces in the y direction are all equal to 0. So if we set this entire equation equal to 0, we will get that the normal force let's write this. Let's move this right here. This is for the weight force. We'll get that the normal force is equal to why did I go to the magnifying? Normal force is equal to 300 and 130.75 newtons. I was looking at the wrong problem in my notes. So the normal force acted upon this suitcase is 130.75 newtons. So if I were to draw that down, you would get 130.75 newtons. And if you add everything back up together, if you add 130.75 newtons, it's going up, so it's positive. And you have the force of the pull, which is 84.85 newtons. And you also have your weight force, which is subtracted by 215.6 newtons. You would get, once you add these all up together, you would get 0. Wait. Okay, I rounded a little bit here, but you would get very, very close to 0. Let me add them all up together. 84.85 minus 215.6. Yeah, this actually equals 0. Never mind. I was right. And since the suitcase is not accelerating in any direction, up or down, the net force equals 0, and this whole thing makes sense. But how about we solve for the acceleration of the case in the x direction? Well, the net force is in the x direction is not equal to 0. So we can't set it equal to 0. We don't have any more hints. But we only just have one known force in the x direction, and that is the pulling force. So you pulling at a 45-degree angle on the luggage case gives you a force of 84.85 newtons. And that's the only force acting in the x direction. So if you were to divide force, if you divide force by mass of the luggage case, 22 kilograms, then you would get an acceleration of 3.857 meters per second squared. And the reason why I divided force by mass was because Newton's second law of motion states that force is equal to mass times acceleration. And if you divide mass on both sides, you get force divided by mass equal to acceleration. So your normal force is equal to 130.75, and your acceleration is equal to 3.857. Final touch, you need to add the direction of your acceleration with just an arrow. So just draw acceleration with the vector symbol on top, put an equal sign, colon, doesn't matter, and just draw an arrow in the direction of your acceleration, or your total acceleration. For the second problem, you have a box that weighs 50 kilograms. And you have two people that are pushing on it at different angles. So you are on the left. So you are pushing straight to the right with an unknown force. And your friend is pushing up and to the left at an angle of 30 degrees at a force of 300 newtons. Now, if you were doing, an exercise or a workout with your friend here, your friend would be pretty dumb to push upwards. But what you're trying to solve for is the normal force and unknown force of the push of the box. Find the normal force and unknown force of your push if the box is accelerating to the right at 2 meters per second. So let's not worry about this for now. Let's not worry about the accelerating part. Let's worry about the normal force, because that's way, way easier to calculate. So if we represent the box as a dot on this free body diagram, we can know that there is a weight force. That's quite obvious. And there's also a normal force because the box isn't falling through the floor. You're pushing straight to the right with an unknown force, so we'll represent that as an arrow with F push. And your friend is pushing up and to the left at 30 degrees from the parallel. So if we were to draw the angle here, it'll be 30 degrees from the parallel, which is here, at a force of 300 newtons. All right, what can we calculate right now to find the normal force? Well, the normal force only accounts for the y direction forces. So F net of y is equal to 0 because the box isn't accelerating up or down in either direction. And what are the y forces in the system? Well, this diagonal force by your friend has a y component of its vector. So we can solve for that. We also have the weight force, and we can actually solve for that quite easily. If you multiply weight equals mass times gravity, if you multiply the mass of the box times gravity, you get 50 times 9.8. So 9.8 is gravity. And then you get a force of 490 newtons. All right, how do you solve for the normal force now? Well, let's write this down first. Let's solve for this y component of your friend's force. So the y component of your friend's force is 300 sine of 30. Make sense? With some trigonometry, you would get the y component of this force vector. And with the weight force, well, the weight force is going in the opposite direction. Notice how this force by your friend is pushing upward. So this has a positive orientation. But the weight force is going downward. So we want to subtract by 490 rather than add by 490. So the direction of the forces matter. Now your normal force, well, your normal force is going upward, so we do plus n. And what you can actually do is set this entire equation, 300 times sine of 30 minus 490 plus n. And if you were to just solve for n here, you would get that the normal force is equal to 340 newtons. So the normal force is equal to 340 newtons. Now, we solve for the normal force, so that's a check. This is a check. It's good. Let's solve for the unknown force of your push if the box is accelerating to the right at 2 meters per second squared. Well, we know Newton's second law of motion states that force is equal to mass times acceleration. So if the mass on the box is, let's write this MA on this side. If the mass of the box is 50 kilograms and the acceleration is 2 meters per second squared, you would get a net force of 100 newtons. So this is equal to F net of y. So there must be a net force going into the right at 100 newtons in order to make this box accelerate to the right at 2 meters per second squared. So if you were to actually solve for this using our known quantities, let's set up the equation. Let's write 100 newtons is equal to F net of y. If you were to add up all the forces in the y direction, well, you have your push force, which is positive, so we're going to leave that positive. So F push is the force of you pushing, and the x component of your friend pushing at a diagonal is also one of the x forces going on. So if you were to find the x component of that, you would get, well, since this is pushing to the left, this is negative, so you would get 300 newtons times the cosine of 30 in order to get the x component of your friend's force. But what you can do is actually add, so you have 100 plus 300 cosine of 30 onto both sides of this equation. So we can actually remove the F net y here. We can remove this because they're all equal to each other anyways. What you can do is add 300 cosine of 30 onto both sides of the equation, and then you get a real number for your F push. And F push, if you add 100 plus 300 cosine of 30, is approximately 359.81 newtons. So you have to push, well, you are pushing at 359.81 newtons in order to resist the push of your friend, and also accelerate the box at to the right at a rate of 2 meters per second squared. So on to the next problem. Wait, I just noticed something. Not on to the next problem yet. You have to write the acceleration vector with your free body diagram. So I just have to write the direction of the acceleration. If the direction of the acceleration is just straight to the right, you just have to draw acceleration with the vector symbol on top, with the colon, and draw an arrow in the direction of the acceleration. Now on to the next problem. So this one is slightly tricky, and it's less of a free body diagram exercise and more of a logic exercise, I'd say. But free body diagrams can help you think of this. So you're in an elevator, hence the 2 cables and the very thin box, and you're standing on a scale, and this scale tells you your weight in newtons. So if the elevator is just at rest, so it's accelerating at 0 meters per second, and it's accelerating at 0 meters per second, and your weight is 1,000 newtons, what will the scale read in newtons if the acceleration of the elevator is what is above, which is 0 meters per second squared? Well, this isn't a trick question because, well, if you weigh 1,000 newtons and you're not accelerating and you're standing on a scale, then the scale will read 1,000 newtons, right? And what a scale does is read the normal force that is exerting on you in order to tell how much is going to be displayed on the scale. So normal force is what matters with the scale, not your weight. So what about now? What if the scale reading in newtons, what would the scale read in newtons if the acceleration is what is above now? So now it is 2 meters per second squared. So you're accelerating upward at 2 meters per second squared. Maybe I should make that more clear with the upward arrow in an elevator. So try to think about this and unpause the video when you have thought a little bit. So let me draw a free body diagram for the scale. So if I represent the scale as a dot, let's draw a free body diagram for the human. Yeah, the human. Okay. You have a weight force, 1,000 newtons, but you also have your normal force. Normal force. Now keep in mind, I drew this, okay, maybe that's not slightly longer. I drew this normal force slightly longer than your weight force, and there's a reason for that. And the reason why is because, well, the elevator has to push up onto you as well in order for you to accelerate upward at 2 meters per second. If the elevator didn't push you up, well, you would just fall, you would just, I don't know, go through the elevator. Like the materials would crumble below you and you'd probably fall to your death. But the normal force must be greater than the weight force in order for you to accelerate upward. So the elevator has to push up onto you harder in order for you to accelerate upward. But how would you solve for that? Well, first, let's solve for your mass. So weight is equal to mass times gravity. And if you just divide 1,000 newtons by gravity, 9.8 meters per second squared, you get a weight of 1,000 divided by 9.8, which is equal to 102.04 kilograms. So this guy's pretty damn bulky. I don't know, muscle, or he's just really tall. But 100 kilograms of pure muscle would be absolutely insane. But this guy's 102.04 kilograms. So why is that important? Well, Newton's second law states, motion states, force is equal to mass times acceleration. Well, if your mass is 102.04 kilograms, kg, and your acceleration is, well, upwards at 2 meters per second, 2 meters per second squared, then your force, the force of the elevator, has to be 102.04 times 2. The force of the elevator to push up against you has to be 204.08 newtons. So this must be the additional force of the elevator pushing up against you in order to accelerate you at 2 meters per second squared. And there also has to be the normal force that prevents you from falling through the floor. So there also has to be a normal force of 1,000 newtons upward, equal to your weight. And there also has to be another force upward. Let's write this a little clearer. This is 1,000 newtons. There's also be another force pushing you up at 204.08 newtons. So remember, the scale reads the normal force it's exerting on you. So if you add the two normal forces of the elevator, well, if the elevator exerts force on the scale and the scale exerts that force back up on you. So if you add the 1,000 plus 204.08 newtons, then you get 1,204.08 newtons. That's what the scale will read if you are accelerating at 2 meters per second squared. And that logically makes sense, because whenever you're standing on an elevator and it starts going up, well, you perceive to weigh more. Like, you can feel the elevator, if it accelerates really fast especially, you can feel the elevator push on your feet a little bit. And if you're standing on a scale, imagine that, if it's pushing up on your feet while you're pushing, if the elevator is pushing up on your feet while you're pushing down on the scale, well, the scale will read more weight. So that makes sense. And vice versa, if the elevator is accelerating downward, you're going to perceive yourself as weighing less. So, as always, if you have any questions, put it down in the comment section. I hope this video helped you understand free body diagrams more.